Okay. Today's seminar is Professor Pavel Fileviez Perez in Case Western Reserve University. And he will talk about new force and dark matter and LHC. So thank you for accepting invitation, and please go your seminar.
Okay, thank you very much, Dr. Miho Kim, for the invitation. I am really very happy to give this talk in Korea, even if it's online talk. Then before I start, I would like to mention that please feel free to stop me anytime. Any question that you have, feel free. And I will do my best to answer any question. Then, as you can see from my title, I will talk about new forces, dark matter, and the Large Hadron Collider. Then before I start, I would like to mention that this presentation is based on my collaboration with many people. My student Elio Golias here, Case Western, my student Clara Murgi, she's now starting a postdoc at Caltech, a postdoc from UC Santa Cruz, Hiren Patel, a postdoc in my group Alexis Plasencia that is here at Case Western. And I will mention some work I did also with Professor Mark Weiss from Caltech. Then let me start in this way. For a long time, we have been thinking about this question. We have been thinking about, is there new physics at the TV scale? No, clearly so far, we don't see anything from experiment, but we have been thinking a lot about this question to motivate the existence of new physics at the TV scale. No? Now, today we know that the standard model of particle physics is a great effective field theory. You know, the Higgs boson was discovered only less than 10 years ago. And we believe that the standard model is just a effective field theory that, you know, where we can actually explain most experimental results that we have. And this effective field theory, you know, when you consider, you can find that you have you can write all possible high-dimensional operators allowed by the case symmetries. However, we don't really know which operators will play role in nature, because could be possible that their symmetries are conserved or broken and they are allowed or not. As you know, we can write the well-known Weinberg operator dimension 5, breaking lepton number, and the dimension 6 operator mediated proton decay, breaking baryon lepton number, and you can write a series of high-dimensional operators. However, we don't really know what is the new fundamental scale or what is the cutoff, the standard model so far. No? Then for a long time, we have been motivating the existence of new physics because the Higgs mass is sensitive to the new cutoff, okay, to the cutoff of the standard model. And this is more or less one of the main ideas that we have been using for a long time to motivate physics at the TV scale. And as you know very well, one possibility is when the cutoff is in the TV scale. Here, what I have in mind is let's think about supersymmetry, where the Higgs mass is really protected by supersymmetry. And, you know, it could be possible that the scale is a TV scale. You know, this is the cutoff of the standard model. However, today, if you think about at least you know, the simple realization MSSA, it's challenging to have a 125 GeV for the Higgs mass. You have to, you know, play, but still supersymmetry could be there in some realization, and still, I personally think that it's one of the best ideas that we have for physics beyond the standard model. If the cutoff of the standard model is very large, let's say that it's somehow connected to baryon lepton number violation. This is the case of classical grand unified theories, where we have embedding of the standard model in a new gauge symmetry. Once you do that, you unify quarks and leptons, and baryon and lepton number symmetries are broken. In this case, if the cutoff, the new cutoff of the standard model is very large, clearly we have to pay huge fine-tuning. We had to think about fine-tuning, and this, you know, maybe it's like that. That will be painful, no? And of course, you can consider other cases. I am only mentioning 3 main cases, where the third case is more exotic, could be possible that the fundamental Planck scale is not very large, it's actually low. What I mean by low could be in the multi-TV scale. You could imagine, could motivate this thinking about large extra dimensions, so any scenario like that, where maybe the fine-tuning problem is not so severe because the fundamental Planck scale is very large. However, all these ideas have been around for a long time, and so far we didn't find any new physics beyond at the TV scale. Okay, of course we know about neutrino masses and things like that, but you know, the relevant scale for neutrino masses could be very high, you know, very large as well. Then regarding the TV scale that we could have access to find new physics, so far even we have been motivating these ideas, we didn't see anything different. Then what I will do today is the following. I will show you that you can consider a set of theories for physics beyond the standard model. And these theories, they actually are just gauge theories as the standard model, and they have to live at the lowest scale. Okay, this is a very strong statement. They have to live at the low scale. What I mean by low scale is below the multi-TV scale. Okay, these are gauge symmetries that they have to live below the multi-TV scale. And therefore, if this is true, as I will discuss, there is a really hope to discover new physics at the TV scale. Okay, this is the main goal of this talk. Okay, then these new gauge theories, they have, before I go to details, I will tell you clearly these are gauge theories, and we know, you know, to study the spontaneous breaking of these new symmetries, we want to have a well-defined anomaly-free theory, and we need, in this case, to have a new sector needed for anomaly cancellation. Okay, it's something very standard. Something very pretty about this theory is that this sector naturally has one of the fields that is needed for anomaly cancellation is actually automatically stable and is neutral and can be a dark matter candidate. Therefore, here you can say that you will get the dark matter candidate predicted from the condition that you want to cancel anomalies. Okay. Typically, as you know, we have a large number of dark matter candidates. Okay, from the axion to neutralino dark matter and many others. Okay. Even in the case of supersymmetry, as you know, you have to impose by hand R parity symmetry to be able to stabilize the neutralino, or even in the case of the axion, which is a very appealing dark matter candidate, still there are other solutions for the strong CP problem that don't require axion. Then even if the axion is very well motivated, could be possible that it's not there. Here, what I will make emphasis is that the minimal theories in these conditions always is predicting a dark matter candidate theoretically, and is defined, is predicted because you want to have anomaly-free gauge theory. Okay, then these theories, as I said, they have to live at the low scale in order to be in agreement with cosmology. Okay, and this is important because if this theory they have to be realized at the low scale, you can think about how to test. Okay. Something interesting as well that in this set of theory, I can predict new violating interaction. Therefore, this is important for baryogenesis, and you can think about the prediction for electric dipole moments. Okay. At the same time, since this theory they have to live at the low scale, I will discuss as well that there are some unique signals that you can think about to be able to test this theory at the Large Hadron Collider. Here I really focus on the LHC because it's the collider that we have now, and we should we should think harder and harder to make sure that we understand how to test any kind of theory. In this particular case, as you will see, there are some unique signals. Huh? Okay, now before I introduce the theories, I don't want to introduce a very, you know, exotic symmetry. I just want to say clearly, you, when you want to think about symmetries that they have to be anomaly free, you could consider different symmetries. But here, I just want to follow the standard model of particle physics, which is, you know, it's the best theory that we have. And in particular, in the standard model, there are symmetries which are not anomaly free. However, I can think about how to define a theory where these symmetries are local symmetry and anomaly free. And the simplest symmetry are, let's say, baryon number, total electron number, and you consider other exotic possibilities, okay? But I don't want to go too far from the standard model. I want to use the symmetry of the standard model, and we like to think about how to define a local symmetry. In this case, I will focus mainly in the case where baryon number is a local symmetry, okay? Baryon number is a local symmetry. You know very well, a baryon number in the standard model is broken at the quantum level by SO2 instantons in 3 units, and it's a no anomaly free symmetry, okay? Then the idea of considering baryon numbers and local symmetry was somehow mentioned by Abraham Pais in 73 in a very short paper. He didn't really think too much about that, but it's fair to say that at least he mentioned the idea, even if in a footnote he said that Stringer somehow mentioned in some talks, okay? And then for a long time, this idea was there. This paper, you can check online, doesn't have more than probably 50 citations. I forgot the number. Clearly, the idea was ignored for a long time. And then a while ago, together with Marwhite from Caltech, we started to think about which are the theories, type of theories that we could write down using the fact that baryon number, which is also a very important symmetry for cosmology, as you know, could be defined as a local symmetry, and how you can define a simple theory where you can have the spontaneous breaking, in particular the lowest scale, without having any problem with any experimental constraint. Okay, and recently we have been working on that, and we will discuss how really all the collider signals so far we have. Okay, then in particular for very young people, students, and young postdoc, let me emphasize how to do that. As I said, I will talk only about baryon number, but you can ask me how to do the job for lepton number or both at the same time. In the papers, you will see we study spontaneous breaking of the both symmetry, and we show that you can do this in consistent way at the low scale. Okay. And then, as you know, again, baryon number is not anomaly free. Then, if you want to gauge, make a local symmetry, you have to remember all the quarks that have baryon number 1/3. And the simple question that you know is how to define anomaly free theory. Okay. Okay, then to do that, you have to do the same thing that you learn from, we do in the standard model. In the standard model, it's amazing theory because in all the degree of freedom that we have is anomaly free. And in this case, when you check all the anomalies, you realize, QCD is Berthold-like. There are other anomalies, U1b with the gravitation anomaly. The only two symmetries that are not zero are this anomaly that is SO2 left square U1b and U1 hypercharged square U1b. Okay, then these two anomalies are not zero. They are equal to 3/2 plus minus. And the question here is, okay, these are the conditions that you have if you want to consider that the baryon number is a local symmetry, okay? And then clearly this doesn't look like a very difficult problem, but at the same time, it's important that the theory that you write down based on the fact that you want to understand the spontaneous breaking baryon number and define anomaly free theory the theory should be simple and should be consistent with everything that we know about cosmology and particle physics. Okay, means that you have to satisfy all collider bounds, and you should not destroy anything that we know about cosmology. And after that, you can claim that you can write a simple, consistent, realistic theory where you can understand the spontaneous breaking of baryon number. Okay. Now, for a long time, we consider many possibilities, like sequential families and mirror families. These solutions are excluded by the Large Hadron Collider after the LHC discovered the standard model Higgs. And the reason is that if you take the standard model and you put the extra family, you will modify the production cross-section of the Higgs in a factor 9, and you will modify the Higgs decay to gamma gamma, and there is no way to have a consistent scenario with, let's say, a sequential family or a mirror family. Okay, and the only solution that today is actually consistent is considering Bertholli fermions, and they don't get mass. The main contribution to their mass is not coming from the standard model Higgs, it's coming from a new Higgs. In this case, the new Higgs will also break the symmetry. Okay, then the three simple theories that we have that we found with the minimal degree of freedom is there is one version that has only 4 extra representations, very minimal. And so, as you will see, one of the degree of freedom is automatically stable and will do the job for that matter. We have considered also a case that you have 6 representation, but after symmetry breaking, you actually have both, in both theory, you have the same degree of freedom. Then the phenomenology and the cosmology in both cases are very different. And then, as I said, this one has only 4 representations. This one has 6 representations, but after symmetry breaking, the degree of freedoms are the same. Okay, and a long time ago, we consider a case that we have a Bertholli family. Okay, then let me introduce the minimal theory. The minimal theory is just, as I said, you take baryon number and you say, I want to consider local symmetry, cancel all the anomalies. In this case, you can cancel all the anomalies, adding only 4 fields. Okay. Here, the nice thing is that the baryon number of this representation is predicted to be plus minus 3/2. Okay, this is very important. It's only 4 fermionic representations. These are psi left and psi r. They are SU2 doublet, normal quantum numbers. This is a triplet of SU2, and this is a singlet of SU2. But the baryon number for these fields are predicted by the fact that you want to cancel anomaly. And this is the minimum number of representation that you have if you don't want to spoil anything and in cosmology, and you want to also be able to generate large masses for them. Okay. Then the Lagrangian is very simple. You can write the Yukawa couplings, and as I said, any extension of the standard model where you have new fermions, these new fermions cannot talk too much to the standard model Higgs, because you will destroy the property of the standard model Higgs. Because the standard model Higgs is very standard model like, then the room to modify the couplings or decay of production channels is very small. Then in this case, these new fields, they actually get mass from the new Higgs that is there to do 2 things: to generate masses for the new fields and to break the local baryon number. Okay, but the fascinating thing about this is that these new Higgs must have a baryon number equal to 3. Okay, cannot be 1, cannot be 2, it's just 3. The reason for that is, you know, anomaly cancellation is predicting the baryon number for this representation, but if you want to generate masses like this from the new symmetry breaking, the only way to have a gauge invariant Yukawa coupling is that the Higgs should have baryon number 3. Okay, this is a hard prediction from the minimal model. Okay, this has huge implications because this is actually means that after symmetry breaking, you never will get any baryon number violating process that actually avoid that you can actually break this at the lowest scale. In this case, you should expect only delta B equal 3 plus minus 3 processes. This means that the proton in this theory is stable. To get proton decay, you have to break baryon number in 1 unit. If you don't break baryon number in 1 unit, you don't get proton decay. You don't get here N and bar oscillation because baryon number is not broken in 2 units. And this is a very interesting thing because as you know very well, many collaborations have been looking for proton decay for a long time. Particular theory, that is the minimal theory, where we can understand the spontaneous breaking baryon number is predicting that the proton must be stable. Therefore, you can say that this is a gauge theory for proton stability, okay? Proton decay is predicted in grand unified theory in a very generic way. We cannot predict so well in grand unified theory because you have to, do a lot of effort. However, it's a generic prediction for grand unified theory. Here, the situation is different. The situation is that if you consider the minimal theory for spontaneous baryon number breaking, spontaneous baryon number violation, the prediction that you get is that the proton is always stable at any level of perturbation theory, and this is the gauge theory for proton stability. Okay. Then this model has something interesting. It has only 4 extra representation, but one of them, the Liles neutral field, is automatically a dark matter candidate. And let me emphasize again, this is predicted from anomaly cancellation. I was not looking for, I didn't put this by hand. I just was trying to build a theory that where I can understand the spontaneous breaking of baryon number, and I get this prediction as a bonus, okay? Typically, for people that like supersymmetry, always we like supersymmetry because we have this extra possibility to have neutralino dark matter. However, it's important to mention that in that case, you have to put extra symmetry by hand, okay? You easily could live in R parity violation without any conflict between cosmology or collider physics or anything. As you can imagine, this in this theory, you have a new gauge boson, electrophobic, doesn't talk to leptons, that could decay mainly to quarks and dark matter. You have a new Higgs boson that could have different decay channels, in particular, as I will explain, the decay to gamma gamma, the direction to gamma gamma, and the dark matter can be large. And you can have very unique signature collider, and everything is connected to the fact that there is dark matter in the theory, and you will have missing energy signatures at collider, okay? Which is, as you know very well, in the case of supersymmetry theory, when you are parity conservation, we always expect, since the neutralino is stable, you expect a huge number of signals with missing energy. Here is actually similar, even if this is a very simple theory. The fact that the theory is predicting a dark matter candidate for anomaly cancellation, and the new sector is isolated from the standard model because the baryon number of the new fermions is 3.5, you will have always missing energy signatures, which are unique in the way that, as I will explain, when you want to predict them. No? As I said, feel free to stop me at any time. Okay. Then something that is very important for here is that this minimal theory is making the prediction that baryon number must be broken in 3 units. This means I never get proton decay. The proton decay bounds are very, very strong then if you have any theory predicting proton decay, the scale relevant for symmetry breaking has to be very large. Typically, as you know, should be the grand unifying scale. No, the fact that here I don't get proton decay, in fact, you predict that the proton is stable, you don't have to worry about proton decay bounds, and then you can consider the fact that the scale for U1 breaking can be very low, okay? And it's important to check how low the scale can be because you want to know if you can test, no? And this is a recent paper where we studied the collection of all the bonds on CMS and Atlas collaboration, where, you know, in this plane you have the gauge coupling associated to baryon number and the mass of the C prime associated to baryon number. As you can see, easily you can live at the low scale, you know, even close to the Letroux scale, without assuming a small gauge coupling, okay? 98% of the extension of the standard model that typically we consider that you know the frame of the standard model, they feel this new force, you have to assume a small gauge coupling if you want to consider lower scale because the collider bonds are very strong. Anything that has a coupling to leptons, you know, the lab bonds are very strong and you cannot have this case. In this case, the fact that the new gauge boson has talked to only the standard model quarks and the new fermions there that needed for normal cancellation, you can live at the very low scale without assuming a small gauge coupling. Means that you can have very large cross section and look for this new gauge boson, okay? And this is very nice. For example, here you can check what is the width that should have this new resonance if you impose, for example, the collider bounds, okay? And you can see the width can be non-small, can be, you know, large. You can 0.1 GV or 0.5 GV is the large width, okay? Then you can, you know, consider many production channels for this C prime, and you can see the cross section can be huge. In particular, CMS has been doing a great job for very low masses. You can have associated production in a plume of a photon, and you can see if this gauge boson is there at the low scale, let's say 300-400 GV or any value, due to the fact that the gauge coupling doesn't need to be small to satisfy the collider bounds, clearly you could see this very easy collider because the production cross sections are large. Then you have to deal with the background and try to do your best to see the signal if this is there, okay? This means that this brings me to the first point. The theory can live at the low scale, and here I try to give you a feeling of what is the kind of which are the bounds that we have for the new resonance associated to baryon number breaking, and means that this theory is a gauge theory that can live at the lower scale. The gauge coupling doesn't need to be small, and the production cross section for this new resonance can be large. Then it's up to the experimentalist to look for that. Okay. Then
excuse me.
Yes.
Excuse me. Just before getting into the next point, I just want to make sure one thing. This baryon gauge boson is not actually a completely leptophobic because of the kinetic mixing with photon and the mass mixing with Z. If you consider one loop, are you assuming some, some tuning on that?
No. You're right. Here, I didn't put the kinetic mixing there. Okay. Of course, you can put the kinetic mixing, but you don't learn too much, because what you will find is that the kinetic mixing has to be small. Okay. Actually, you can check the appendix of this paper. We studied the bounds on the kinetic mixing. And, you know, if the kinetic mixing is smaller than 10 to the minus 2, 10 to the minus 3, you can satisfy all the bounds. But this is this is the problem in any abelian gauge theory. You can always have a kinetic mixing, you can put the bound, but you don't learn anything about your theory because this is just an extra parameter there that doesn't do anything. This question is better if you have a UV completion where you can actually compute clearly this kinetic mixing, that will be something more interesting. At this level, you can put your kinetic mixing, and the only thing that you can say is the kinetic mixing has to be smaller, but you don't really learn anything about how low the scale can be.
Yeah.
My point is that it's important to know how low the scale can be. Here, without assuming any small gauge coupling, you know, a gauge coupling is something, it's very important because it will define all the cross sections. Doesn't need to be small, and the gauge boson can be at the low scale. Okay. Now regarding, you can consider one loop induced, but that is typically very small, and we actually compute that this is very small as well. Okay.
And and also how about mass mixing with Z? Because you can't.
There is no much. There is no much. Oh,
Chi-L from, you know, what I'm thinking is that you have a Chi-L, Chi-R Higgs, Higgs coupling, and you know.
Well, here the Higgs breaking U1B is a singlet on the standard model gauge symmetry. Then when you break U1B, there is no mixing. The only mixing will be loop induced, and this is very small.
Yeah, well, then yeah, what I'm imagining is that the mixing between the Navier-Stokes boson of Higgs, standard model Higgs, and Navier-Stokes boson of Z sector, the boson baryonic sector.
Right, but the point is that this doesn't happen at 3 levels because.
Oh yeah. I'm talking about one. Yeah, I'm talking about one.
Yes. This is the same thing as kinetic mixing. You can compute. You can see in the appendix of this paper, but it's very small. It's very, very small.
Sorry, can you say what do you mean by very small? I mean, we've got new states charged under hypercharge and baryon number, so I would expect to be 16 squared, very small.
Very small. I mean, it's below 10 to the minus 2, and then I don't have the plot here. It's computed there. Basically, I agree with you. You have, let's see, you can consider the loop where you have the new Fermi wing SO2 quantum numbers and baryon number. That gives you something way below 10 to the minus 2. Okay, you have the loop factor, but when you have, there is you have to put the numbers, it will be below 10 to the minus 2. That value is small enough to satisfy all the collider bounds. Okay, remember that remember that if you take, just to give you an intuition, if you take any U1 prime symmetry and you put the kinetic mixing with QED, and even if the new gauge boson is very, very light, typically the bound that you get is like 10 to the minus 3, even if it's really light. Okay, here I am talking about something that is electroweak.
No, sorry, that's not true at all. You get bounds down to 10 to the minus 15 or so. Of course, if you're living at hundreds of GeV, then I think you're right. You have 10 to the minus.
I am talking about something that is massive. I am talking about something that is massive. Okay, generically, again, depends a lot where you live. If you are at the TV scale or you are at the electroweak scale, you have to put the bounds. What I want to say is that this loop contribution doesn't really provide any strong bound. This is actually, these bounds are not so weak. It's weaker because there is no interaction with leptons, okay? And the interaction with lepton will be induced by one loop as also the suppression of the massive CV gauge boson. When you put all the things together, the lab bounds don't provide something that is stronger than this direct LHC bound. This is what I want to say. In particular, CMS did something pretty impressive, is that this is a monojet searcher with the CV together. And these particular bounds actually used to be the left bounds were better, but these green bounds here that you see are associated production CV with monojet. These are really way better than any left bound. Okay. But again, I agree, depends where you live. What I wanted to say, when you put the numbers, these bounds are better than the the one loop induced cross section with leptons, let's say. Okay, but I invite you to see the appendix of this the paper anyway. Okay.
Above the CMAS, I certainly agree.
Oh yeah. Of course. In any case, you will see now for the symmetry breaking scale, unless you assume something, the new fermions that are getting mass from the new symmetry breaking scale, then they cannot be below the electroweak scale. Okay. Then it's not a surprise to imagine this theory has to live about the electroweak scale. Okay. I am not even thinking about that. I just try to show you which are the current collider bounds, and in particular, the present CMS bounds for me are relevant. Okay, I am not looking. Here doesn't make any sense to consider something below the electroweak scale, because you have to imagine if you do that, the new fermions getting mass from symmetry breaking, they cannot be heavy. Then this doesn't make any sense. Okay. Okay. Very good. Thank you for the question. This is very important. Help me to go beyond the discussion. Okay. Now, one of the things that I was talking about is that these theories are predicting dark matter from anomaly cancellation. Okay. And again, this is something that I personally find very appealing, because when we brought this theory, we were not thinking about dark matter for any reason. We just were thinking about the spontaneous breaking barrier number. And it's nice to see that you can get as a bonus a dark matter candidate there. Okay. Then let me explain this very quick. As mentioned, these are the 4 fermions I needed for anomaly cancellation. Here, when you break barrier number by the back after SV get the back expectation value, the U1B is actually broken to a C2 symmetry that is actually protecting the Liles neutral field in the theory. I don't know for people, I know that several of you have been did work a lot on supersymmetry. I would like to invite you to check the quantum numbers of this field. These are like Higgs-Sinus and Wino, and the Vino in supersymmetry. These are the same type of the same quantum number on the SO3, SO2, and U1 hyperchar, but the barrier number here is predicted for the new fermions. Then everything that you know about neutralino dark matter, you could apply to these theories. Okay, but let me emphasize again. Here, I don't impose any C2 symmetry. The U1 symmetry is broken to a C2 symmetry. Okay. And again, the dark matter candidate is there because anomaly cancellation. Okay. Then this is the mass matrix for the neutral states in the theory. As you can imagine, this is a 4x4, and the only prediction that you can make here is that the Liles neutral state in the theory has to be stable, and the C2 is protecting that. Okay, and this is why it's a good dark matter candidate. Okay, now the question is now, okay, let's see. As you know, there are like there is a large number of dark matter models, and all of them are, there are different ways to motivate them. Let me emphasize again, here I was not looking for any dark matter candidate. This is coming from the theory. And I call this, has to, in this case, the minimum model has to be Majorana. And this is, I call leptophobic dark matter because, as you know, the ZV gauge boson will define how this new dark matter will annihilate and do everything, direct detection, everything. And you will have here the interaction for the CV. I will consider mainly the case of you have the dark matter is a chi-left like, due to the fact that this is the singlet, and I would like to see in particular how I can live at the lower scale. If you consider the other cases, if you are in the limit where this is doublet like, the doublet has interaction with the Z, and then the direct detection bounds are so strong that it's impossible to have a simple scenario in this case. In this case, I will assume for simplicity that the lightless neutral field is single light. This is interaction with the ZV, and the CV has an interaction to quarks, defined by the baryon number of quarks. And of course, there are two Higgses, the standard model Higgs and the new Higgs, the physical Higgs. But the important thing is that these couplings are defined by the mass of the dark matter, because the dark matter is getting mass from symmetry breaking, and it's a Majorana particle. Okay. These are all the possible annihilation channels. Okay. And then, as you do in any dark matter study, you want to understand if you can explain the Rayleigh density in agreement with direct detection bounds. Okay. Then we did this study, and then you consider all the annihilation channels. Okay. The model is simple because it doesn't have so many parameters. Okay. You have the mass of the new Higgs, the dark matter mass, the gauge coupling, the mixing angle between the two Higgses, pretty much everything. Okay. Here I will give you one example just to give you a feeling which are the different, what is the importance of the different channels. Here the color code means that, for example, let's say this blue here means that in this area, in this in the plane, the mass of the CV and the dark matter, the main channel is the annihilation to two gauge boson. Okay. Here, for example, the main channel is the resonant Kikri bar, and here, for example, the main channel is annihilation to the CV and the Higgs. The important thing is that the CV, when the second Higgs, the coupling to the dark matter is actually proportional to the dark matter mass. And then when you increase this dark matter mass, you will increase that coupling, and that cross section can be actually very important. Huh? And this line here is actually when you impose the perturbative bound of the Yukawa coupling that is associated to the dark matter mass, you realize that you cannot be below this line. Okay. Typically, in any dark matter model, you will hit the perturbative bound at the 100 TeV, naively speaking. But here you will, the fact that the dark matter is getting mass from the same Higgs that is breaking the symmetry, there is a bound coming from perturbativity that will tell you that the mass of the Higgs, the mass of the dark matter cannot be larger than this value here. Then, why this is relevant? Well, you can consider different scenarios, and then we know that in a model independent way, the well-known unitarity bound for dark matter model will give you an upper bound around 100 TeV. Okay. Then here, what you can do, you can take the model and change all the parameters in the theory, and find that, let's say here, for example, I have the same result in the same plane, the mass of the CV and the mass of the dark matter, that tell me that if the gauge coupling associated to baryon number is very large, okay, in this case, I don't want to go beyond, because I will, I am just hitting the perturbative bound even for the gauge coupling, due to the fact when you had to check all the couplings in the theory and make sure that any of the couplings in the theory become non-perturbative. You realize that you can live in this line here or in the resonance, but the important thing is that the perturbative bound coming from the perturbative bound on the coupling that define the dark matter mass means the dark matter mass is a coupling, you call coupling times the background expectation value SB. This particular coupling become not perturbative if you are below that. This means that the theory has to live below that particular value here. Okay, Here, maybe in the eye you cannot see, but it's a little bit more than the resonance, but the resonance is competing very much, okay? Means you cannot go forever, okay? Because so if you go forever, or you could have the situation that you overclose the universe, or you will break the perturbative bound for the Yukawa couplings in the theory, okay? Again, as I said, the unitarity bound for dark matter model is naive because it's very generic. So if you are in a given dark matter model, you have to check all the couplings in the theory, make sure that you are perturbative, and also imposing the condition that you don't want to overclose the universe, means that the Rayleigh density is no larger, okay? Then when you do this study, you realize that clearly there is an upper bound on the mass of the CV. Then the mass of the CV for me is the scale, the new symmetry breaking scale. Okay, if you because it's the physical, it's the physical gauge boson that I could discover a collider. If we discover that the fact, if the theory is realized, the fact that all the fermions are getting mass from the same symmetry breaking scale, the new fermions, and they say both mass, I can use CV as the physical scale. Okay, it's more physical than talking about a back expectation value. Anyway, you can do the both, but here the mass of the CV cannot go beyond like a 28 TV. Okay, and this is very important because I was talking about the you have this CV gauge boson there. The mass could be around the Fileviez scale, and this is consistent with all collider bounds. And in particular, let me emphasize again, you have to generate masses for large masses for the new degree of freedom, the new fermions. They don't have color, but they have SO2 quantum numbers. They have electric charge, means they have to be above the Fileviez scale, and therefore all these fermions and the CV, they could be at the around the Fileviez scale. But when you do the dark matter study, you realize that the Rayleigh density constraints plus perturbative bounds on all the couplings, in particular the perturbative bound on the Yukawa coupling for the dark matter, the Yukawa coupling between the dark matter and the new Higgs, tell you that the scale cannot be above 28 TV if you want to be very quantitative, okay? And of course, you had to worry about direct detection. As you can imagine, direct detection here, this is a Majorana dark matter. You have interaction through the ZV and the both of the Higgses. The Higgs part is suppressed by the mixing angle, and we have some bounds on the mixing angle is coming from Higgs physics. And however, this is velocity suppressed because you know this is a Majorana dark matter, no? And then you can do the study. I can show you a case that when the new Higgs is at 200 GeV, I am using here GeV 0.1 because 0.1 in the plot I show you, always you can satisfy all the collider bounds in that regime. You can see that easily you can satisfy the signal 1 ton bounds if you are above, let's say 160 GeV for the dark matter mass, changing for various different mixing angles. However, let me emphasize something that I will use later. Below 170 or 60, the mixing angle has to be typically below 0.1. Okay, the collider bound that we have is around the mixing angle should be below 0.3. Just from high precision of the Higgs. In this case, there are only 2 points. I just wanted to say easily you can have the dark matter can be at the low scale. You're consistent with direct detection bounds because it's a Majorana particle. The scattering cross section with the nucleus is velocity suppressed, and the mixing angle can actually have the different values. If you want to be at 0.3, of course, you have to live above even 500 GeV, okay? But if you are, let's say, between 0.1, 0.3, you can actually be in different scenarios where easily you can satisfy the Sino 1 ton bounds, and Sino n ton can actually cover a lot of the possibilities in this case, okay? But a simple, the simple conclusion is that you can have the theory is predicting a dark matter candidate, and once you impose the condition that you don't want to overclose the universe, and you impose all the perturbative bounds on all the couplings in the theory, you realize that the theory has to live below the multi-TeV scale, okay, below, let's say, 30 TeV, no at the GAT scale, no at the 100 TeV scale. And everything can be consistent with all the experimental bounds coming from direct detection, okay? Only because, in particular, because you can live really at the mass of the dark matter can be close to the electroweak scale, because it's a Majorana dark matter that talk only to the coupling to the CV is just type Majorana, and the cross section for direct detection will be velocity suppressed. Okay, and here the first point I really want you to emphasize is that the scale for baryon number violation, you know, typically, historically, we always think about the scale for baryon number violation, thinking about the classical grand unified theory where the baryon number is explicitly broken when we unify quartz and lepton on the high scale. Here, the most important point is that you can build a simple theory for a spontaneous breaking of baryon number, but the fact that the minima theory is predicting a dark matter candidate, once you impose the dark matter constraint, Rayleigh density and direct detection in a consistent way, the theory has to live below the multi-TeV scale. Okay, this is a very important thing because 95% of the theory that we have for physics beyond the standard model, the scale can be anything. You can push everything to the Planck scale, and nothing happens. Okay, typically we didn't like to do this in some theories because we try to follow some arguments about fine-tuning, but fine-tuning is not a physical argument. We don't really know what is the meaning of fine-tuning. Or if we understand what is fine-tuning, but we don't really know if this is the principle that we have to follow to, you know, to predict a discovery or something. No? Okay, this is a very important thing. The theory can live at a very low scale because collider bounds are weak, but there is upper bound, the symmetry breaking scale, that is actually multi-TeV. Therefore, there is a way to test or to rule out the theory. You don't have to go all the way to Planck scale or anything like that. Okay. Okay. Now, recently, actually, in our last paper, we want to go beyond and try to understand. For example, there is a new Higgs breaking the local baryon number, and at the same time, it's the same Higgs that give mass to the dark matter candidate material. No? Then we want to see cosmology is motivating the fact that the theory has to live at the low scale, and then let's think about how to test that, what are the signals of this new Higgs I call baryonic Higgs because it's the one that's breaking U1b. And I will discuss something that I find fascinating is that in some scenarios, the branching relation to photons can be very large. When I say very large, I mean compared to the standard model prediction of the standard model Higgs, or the branching relation to dark matter can be very large. And this is very important for the different studies looking for missing energy at collider. Okay. Then, as you know, Atlas and CMS have been looking for a long time for invisible decays of the standard model Higgs. Okay, and the bound is actually pretty good. The branching relation has to be below 0.13 for the standard model Higgs. And here, what we have is again the standard model, the new sector, and the new Higgs that will mix on the standard model Higgs But at the same time, these new Higgs give mass to the standard model. Okay. And again, the C prime is something that the standard model force are filling with large coupling, because the gauge coupling doesn't need to be small in this case. Again, of course, there are other models where you have a C prime and gauge coupling, but you don't even can motivate the fact that they can be large in a simple way. It's different. Okay. Now, these are the possible decays. As you can imagine, you can have decays to all the standard model particles. You can decay of a photon CV, and you can, the new CV. Here, for me, this is the dark matter candidate. And this is the new fermions. Let's say the dark matter is always the lightest field in that center, and the capital F are the new fermions. Okay. And then, since the theory is so simple, and again, the dark matter is getting mass from the same Higgs, you can do something that we typically like it to do in supersymmetry. The point supersymmetry has, the FSSA could have so many parameters that you never can make a prediction. But assuming some supersymmetry schemes like gauge mediation or M-Sugra or things like that, for a long time, people study the predictions of the different signatures in supersymmetry when in agreement with cosmological bounds. Here, the theory is so simple that you can actually study the correlation of different scenarios for dark matter annihilation that give you an agreement where you know that you don't overclose the universe, and the Higgs decays. Okay. And this is what I will do now. As you know, these are I mentioned before, these are the dark matter annihilation channels. And let me emphasize again, let me think about a light Higgs, 200 GeV, okay? If you are in this region here, the main channel is the annihilation to QQ bar. Then if you are here, the main annihilation is CV to CV and the new Higgs. And here there is a small portion that is CV-CV. The green lines are excluded by one tone, where you match the exact Rayleigh density. This is what you will exclude for if one tone achieve these predictions. These are projections from n tone, and the rest still we don't know if we will cover. But this is in a simple way. These are the kind of main scenarios that you have for dark matter annihilation in a consistent way. You could be in the resonance. You could be in a scenario where the main annihilation channel is to CV, and you could be in the case where the main annihilation is to CV HP. Okay, these are like the three main scenarios for light Higgs. Okay, as you know, LHC cannot will not discover something that is very heavy. Then I want to focus on in the scenario where the Higgs can be actually light. As I mentioned already before, the direct detection bounds are very important, but easily you can satisfy the bounds here. In particular, let's say here, this is 200 GeV. Clearly, anything that is below here is excluded by 1 ton. Okay, this means that if you consider this light Higgs, clearly you never will be able to decay to dark matter, because this possibility is excluded by 1 ton. Then you start seeing the correlation between the different the two things, the Higgs decays and the dark matter constraints. Okay, then these are the three main scenarios. You could be in the resonance. I personally don't like too much because this is so peculiar, the resonance. You could be, the main annihilation channel could be to CVHV, kinematically when this channel is kinematically allowed, or you can annihilate to CV, okay? Then you study the Higgs decays. Means, for example, you know very well how to compute the Higgs decay in the standard model. For this new Higgs, you will have the same. However, the new fermions in the theory, they also induce one loop decays, okay? Then here in this study, we consider the one loop contribution to all the possible decays, okay? And then this is a possibility, okay? Then two, studying in general way how these decays can modify. Then, for example, in the first scenario where you have to live in the resonance in order to make sure that you achieve the right Rayleigh density, and the Higgs is very light, like 200 GeV. These are the values that you need to have a consistent. This is just one particular scenario where the CV, if the CV has this value, you satisfy all the bounds, direct detection, the collider bounds in the CV, everything. Then this is the Bryson equation, the Higgs versus the mixing angle. The mixing angle is a free parameter, the mixing angle between the two Higgses. Therefore, you should vary it to see how the prediction changed. And then you find something that is similar to what we know in the standard model. In this case, the decay to WW is a dominant one, okay? However, the gamma, the Bryson equation to gamma is way above 10 to the minus 2. If you remember, the Bryson equation of the standard model Higgs to gamma is 10 to the minus 3. Here you are way far above, okay? And this means that this theory, if you are in the scenario where, in scenario 1, where the main annihilation channel is through the resonance, in a generic way, you will get that the Bryson equation to two photons, this red line, the Bryson equation can be actually way larger, more than a factor 10 if you compare to the standard model, okay? Here, this part of the parameter space is actually excluded by Sino 1 tone, okay? Because here you have to make, again, every time that you put input parameter, you have to see that you are predicting the Rayleigh density and the direct detection. And this part will be excluded by Sino and tone, okay? Again, this is an interesting scenario, even if you have to live in the resonance. One scenario that I personally like more is the case that if this is the main annihilation channel, you don't need to be in any resonance. Then if the Higgs is 200 GeV, as you can see, also the Bryson equation for gamma can be very large, okay? Still the WW will contribute, and for largest mixing angle, the new Higgs will follow, let's say, the prediction of the standard model, because you will couple more and more to the standard model gauge bosons, and they will dominate, and of course, the bottom part and so on, okay? But notice that the prediction here for C gamma and gamma can be actually pretty large, okay? Again, C gamma is also very tiny in the standard model, okay? And as I said, let me go, as I said, this part of the parameter space is excluded by Sino 1 tone, and in yellow, everything can be tested by Sino and tone. Here, if you go beyond, you actually, this scenario is this scenario is totally excluded by Sino 1 tone. Okay, in this case, if you go in the CV mass lower, means that you want to open the other channel into 2 CV, you actually realize that this is excluded by direct detection experiment. Now, let me give you, this is the case where the new Higgs, the mass of the new Higgs is 200 GeV, means that you can imagine that the production cross-section will be large, and you can look for these channels. And the conclusion is that once you put you study the interplay between the Higgs decay prediction, the Rayleigh density constraints, you realize that the Bryson equation to photon can be very large, okay? Now, if the Higgs is, the mass is larger, 500 GeV, clearly in this case, the situation could be different. Could decay to dark matter in agreement with everything. Then the Bryson equation to dark matter is actually 100%, okay, pretty much. no 100, but close to 100. And of course, once you start increasing the mixing angle, the other channels will be very important. But even here, before you hit the bounce from within 1 ton, the invisible width can be actually pretty large. Okay, and also if you consider a lighter C prime, there is an interplay between the branching relation to dark matter and the branching relation to CV, but still the branching relation to dark matter is 0.1, still very, very large, okay? And this is interesting because this is pretty much what you can see. Of course, you can consider a Higgs 1 TV, but it's very hard to have a large cross-section to produce the Higgs in such a way that you could have a large number of events, and then when you do the full collider study, you can actually make a claim. That's why I emphasize these two main scenarios. In one scenario, when the Higgs is around 200 GeV, the branching ratio to photon-photon can be very large. When the Higgs is around 500 GeV, you can have consistent scenario in cosmology, in direct detection relative density, where the branching relation to dark matter is very, very large. Okay. Then I hope that I am not over time. How much time I have?
Still okay until 11:30. But it maybe.
No, it's fine. I still have. Okay, good. I just wanted to make sure that I knew.
Okay.
Okay, very good. Thank you. Now, the main point again is that this model is so simple that you can study the correlation between Higgs decays and the dark matter constraints, relative density, direct detection. And as I mentioned to you, there are two main scenarios. If the Higgs is light, around 200 GeV, the branching relation to photon can be very large. And if it's heavier, the branching relation to dark matter can be actually order 1 as well. Okay, or maybe 0.1, depends on the mass of the CV. But even if you open this completely, the CV dedicated to 2CV is completely open kinematically, the branching relation to dark matter is very large. Okay. And now you can think, okay, how do I look for the baryonic Higgs at the Large Hadron Collider? Okay, you know that the CV can be light without assuming a very small gauge coupling. Again, when I say light, I am thinking at the electroweak scale, above the electroweak scale. Okay. Then, as you know, for any model where you have more than one Higgs, you always have the possibility to use the standard model production channels to produce the new Higgs, right? So the mixing. Here, if you consider a light Higgs, where still, let's say, the glue friction production cross-section is large, direct detection experiment will tell you that this mixing angle has to be below 0.1. Therefore, you will have a suppression for the user channel, no? Then here, let me emphasize, the theory is also give you the possibility to have a new production channel for the Higgs that is not suppressed by any mixing angle. Because if you consider KQ bar CV, this is a gauge coupling, doesn't need to be small. You can actually have the associated production HBCV, where the gauge coupling doesn't need to be small, the CV can be light, the HB can be light. Therefore, you can have large cross-section to have the associated production for the CV. One other thing that I would like also to emphasize, in the beginning, when you write the theory, you have the impression that the CV could decay to quarks, also to dark matter. But once you you study the different scenario for relative density and direct detection, you realize that the CV can decay only to quarks. Okay, means that you can predict very well the width of the CV. Okay, because if could decay to dark matter, depends which is the dark matter mass. But no, once you do the study for relative density, you realize that the CV always will decay only to standard model quarks. Okay, and again, you can have a production channel where you produce together the HP and the CV, and the cross section can be actually pretty large. No? This is the production cross section proton CV HP at 14 GeV, assuming the Higgs mass is 200 GeV, and then these are the different values. Okay, GeV in the CV plane, and then when you put all the jet bound coming from the ZV searches, okay, the collider bounds on the coupling and the mass of the CV, the fact that you can produce, you have the use, so these are the bounds I mentioned before. You actually rule out everything that is in gray, okay? But you can see, you can have a scenario where the cross section can be large, okay? And now, knowing that for light Higgs, you can say, okay, if the production cross section for the associated production, the Higgs and the CV can be large, I can now study the different signatures from the different decays and try to estimate the number of events that I get from different channels. Okay, then this is, for example, when I have TT bar gamma gamma. Remember, I told you I can, when the Higgs is light, the Bragg relation to gamma gamma can be very large. Again, what I mean by very large is more than even a factor of 10 what you have in the standard model. And then in this case, CV can decay to TT bar, so the CV is actually heavy enough to do that. And then you can have a scenario. Here you have to specify the values of the other fermions because the fermions for anomaly cancellation, because here we are predicting all the channels also on one loop, putting one loop correction for every decay channel. Then you have to do that. Then if you have large luminosity, okay, you can actually achieve a large number of events for the TT bar gamma gamma. Okay, I know that this is the prediction having 3,000 inverse femtobar, but this tells you that if the gauge coupling is not so small and the CV is around, let's say 400 or 500 GeV, you could have a large number of events for that. Okay. Something that is more interesting is the Higgs is around 500 GeV. The new Higgs mass is 500 GeV. You could have the order one Bragg relation to dark matter from the Higgs. You have the TT bar channel, and you can actually have a large value for these signatures, number of events for different scenarios. Therefore, it means that one can really hope to see this missing energy signature and collider if the Higgs is light enough. Okay. Then this is pretty much. If you have any question, feel free to ask. This is very much what I wanted to discuss about the correlation between Higgs decay and dark matter, because again, let me emphasize the theory is predicting a dark matter candidate for anomaly cancellation. The new Higgs that is there is breaking the symmetry and giving mass to the dark matter at the same time. And then when you do the Rayleigh density study and the direct detection, you find that there are only 3 main scenarios for Rayleigh density that are in agreement with direct detection. And then when you study the Higgs decays, you can put everything together to understand how large the Bragg relation of the Higgs could be. And then what you find is that if the Higgs is light enough, or the mean light enough is close to the Letroux scale, 200 GeV, the Bragg relation to gamma gamma can be actually very large. Okay, when you go and start increasing the Higgs mass, you can have a Bragg ratio order 1 to dark matter if due to the fact that when you increase the Higgs mass, you avoid all the direct detection bounds, and but still you can do the job for Rayleigh density. And then when you put together everything, these are the two main scenarios that you can have. Okay. Now, you can do more in this theory. In particular, for a long time, people were asking me if you have a spontaneous breaking of baryon number at the low scale, what happened with CP violation, what happened with baryogenesis and things like that. Okay. Then clearly, in this theory, you have also, you predict the new couplings, the new interaction that you have due to the fact that you have this new 4 extra representation, allow you to have more CP violation in the theory. However, this is something also interesting because you will have extra CP violation that you need for, let's say, for baryogenesis, but at the same time, you have to make sure that everything can be consistent with EDM. Here there is a small typo, electric dipole moments. And this is important because, again, as I said, the scale of symmetry breaking or the mass of all the new fields cannot be too large. EDMs can prove very large scales. Therefore, you cannot really, the fact that these new fermions cannot be too heavy, okay? You have to check what are the predictions for electric dipole moments and the CP relating phases that you will need, let's say, for baryogenesis, and make sure that everything is, you can be in agreement with all the predictions, okay? Then, again, the theory predicts new CP violating phases. What I mean by that, you take the Yukawa couplings and you try to redefine all the fields, and you realize you cannot remove all the phases, okay? In a more common notation, I try to repeat everything. These are the Yukawa coupling, the Higgs. These are the new physical degree of freedom, the CV, the HV, the charged fermions, and the neutral fermions, okay? And then if you take, let's say, the mass matrix for the charged fermions, they look pretty similar to the Charginos in supersymmetry. And then you try to redefine all the fields to see if the still in general way this Yukawa coupling can be complex. You realize that there is one phase which is has this combination that you never can rotate away. Okay, and this is the first indication that there are new interactions there, and they in a general way they can break CP, and this is the phase that you never can rotate away. Okay, from this sector in charge of fermions. Okay, now this means that better you check the prediction for DM and make sure that everything works. In particular, recently the ACME collaboration in 2018 found a spectacular upper bound on the electric dipole moment for electron, which are actually very, very impressive. If you are not familiar with this experiment, I really recommend you. It's a beautiful experiment that typically when I teach EM, I talk about this experiment. In this particular case, if we think about how to generate the electric dipole moment for the electron, in this particular model, you will have the well-known C bar contribution that through the standard model Higgs and the new and the photon, the Z and the ZV in this case, you can generate a two-loop contribution to the electron ADN. Okay, you know, you will think that this is small, but no, not really, because remember that these are gauge coupling. You can have a photon here, and when you actually put the calculation, typically you will get very interesting bounds. No? In particular, again, if you do this in a theory where these fermions can be at any scale, okay, clearly you will satisfy this bound very easy. But this is not the case here because I explained that Rayleigh density constraints together with the perturbative bounds on the Yukawa coupling for dark matter with the new Higgs. tell you that the new symmetry breaking scale cannot be too far away from 30 TeV, okay? Then it means that all the fermions, including the CV and the new fermions there, they cannot be far away from that scale if you want to satisfy a perturbative bound for all the UCAR couplings, okay? If you do a simple estimation, these new fermions, they cannot be above 40 TeV. Again, this is a very conservative, very conservative upper bound on these masses. Clearly, they can be close to the Letroux scale, 300 GeV, 400 GeV. They could be any scale, okay? Here, the interesting thing is that cosmology together with perturbative bounds tell me that this new degree of freedom cannot be too heavy. Therefore, if the phase, the new relevant phase for CP violation here is not small, you could expect good bounds from EDMs, electro EDMs. Okay. Then you actually can do this study. This is the value for electro EDM. These are basically the mass of the charger fermions. These are actually the diagonal contribution, the main contribution coming from the U1 symmetry breaking scale. And then assuming maximum value for the, let's say, the phase and some value for the Yukawa coupling, you can see that the current experimental bounds are excluding everything here, okay? If, of course, I am in this scenario when maximum CP violation, and let's say large Yukawa coupling, okay? It means that if this is the case, the new generation of Ahmed 3 could actually really prove most of the parameter space in this case, because as I said, I cannot go beyond like 40 TeV for these new fermions, because I will be in trouble when the cosmological bounds are on the dark matter Rayleigh density or perturbative bounds in the Yukawa coupling of the dark matter. Therefore, everything here should be excluded by dark matter bounds, and then it could be that the new generation for the Ampere experiment could be actually proof large fraction of the parameter space. Or in other words, unless there is a suppression on the Yukawa coupling in the phase, this theory tells you that you should expect generically large value for the electron EDM, because the mass of the new fermions cannot be too large. Of course, you don't know if the phase is large or not, but this is the prediction that you have. Typically, in any model, you have two problems. You don't know what is the value of the phase, and you don't know what is the mass of the new fermion. Here, you have an upper bound the mass of these new fermions. Therefore, you can, if the phase is large, you can expect a large value for EDMs. Okay. Then this is also a discussion for the correlation for the quartz. If you lower the mass of the value of the phase, clearly, you can go down to 10 TeV, but this is pretty much the same result. Okay. Then the important thing is that generically speaking, once you cancel the anomaly with this 4 extra representation, you write down all the Yukawas that are allowed by asymmetry, you realize that you cannot rotate all the phases. Then generically you have phases there that can give you a large value for EDM. And then due to the fact that the new fermion in the theory must be below the multi-TeV scale, if the phase is order 1, you could imagine that this experiment could prove a large fraction of the parameter space in these theories, okay? And this is a very important result if you want to study, for example, baryogenesis in this models, okay? Then you will see a new paper that I will mention here. One of the things that many people, when I started thinking about the theory, thought that was very difficult is to do baryogenesis. Then I wrote a couple of papers on baryogenesis, but I just want to mention one study that we will publish soon. But even before, together with Hiren Patel, we studied the chemical equilibrium equation for all the chemical potentials, and assuming that even the U1B is broken at the low scale, there are new Sfarran conditions for the chemical potential, but then in this case, the fact that the dark matter is a Majorana fermion, there is no asymmetry in the dark matter sector. It's, everything, the relative density is always due to the symmetric part. However, you can actually do the same study that we do in the standard model. If you generate the B minus L asymmetry, a primordial coming, let's say, for baryogenesis, you can compute the conversion factor, putting all the conditions, the chemical on the chemical potential, and show that without any major issue, the conversion factor that you get in this case, if you generate the B minus L asymmetry, the baryon asymmetry is a conversion factor that is actually pretty similar to the standard model. And then this story doesn't change too much, at least in the minimal theory. In the other model, when 6 representation, when the dark matter is a Dirac fermion, you can have you can convert the B minus L asymmetry to asymmetry in the dark matter center and baryon asymmetry. Then, in the simplest case, if you consider, you know, the same degree of freedom that you have in this theory, if you give a lepton number, this is enough, together with the right-hand neutrino, it's enough to cancel all the anomaly for U1L. Okay, this is no, U1L is not like B minus L. B minus L is trivial to cancel the anomaly with 3 copies of right-hand neutrino. For U1L is similar to baryon number, but here you're lucky that the same 4 fermions, if you give a value for also 3.5 for the lepton number, you can cancel, and then you can study the spontaneous breaking B and L even at the low scale. Here, assuming something like a vanilla leptogenesis without assuming any resonant leptogenesis, this is like the lower bound that we find from leptogenesis 10 to the 10, if you want. And as I said, the U1B breaking scale should be below like around 10 TeV. And then you can actually show that in a nice way that leptogenesis can generate the B minus L asymmetry in the usual way, you know, from the out of equilibrium case of the right neutrinos. And the only new thing here is that the conversion factor is different from the standard model, plus the Boltzmann equation should consider the fact that it's a new C prime involved. And then you can actually check the baryon asymmetry. But this is something that you will see soon. Generically speaking, I just wanted to mention that even if baryon number is broken spontaneously at the low scale and must be broken at the low scale, you can have different consistent scenarios for baryogenesis, even vanilla leptogenesis. Okay, then let me summarize. I believe I am on time, right? Then my summary is the following. The most important thing for me to emphasize is that there are many theories for physics beyond the standard model. And often, or more than often, we have the problem that we never can have a very strong argument in favor of having that new theory at the TV scale, because I always can push the new physics scale. Supersymmetry for a long time was the best idea we had, but even today we know that we need fine-tuning if we want to have a 125 GeV mass. I can be more explicit about that, but I'm pretty sure you're familiar with that. And here what I like about this is that this is a very simple theory where you understand something very simple, the spontaneous breaking of baryon number. And when I put cosmology, all the cosmological constraints in the context of the very minimal model, tell me that the theory has to live below the multi-TV scale, okay? And this has a scientific value because it means I could test or I could rule out clearly, I can hope to do that. A theory that is realized at the God scale or the Planck scale, we never will know if I can test this theory, okay? Then a very important thing is that once you write the minimal theory for spontaneous baryon number violation, you actually predict that the baryon number is broken in 3 units, you never get proton decay. Means that this is a gauge theory for proton stability. It's the only one that I know. This is a very strong prediction. It's also even more interesting. In the standard model of particle physics, the baryon number is broken in 3 units by SO2 instantons. Here you are getting that the amount of symmetry, the amount of breaking is also in 3 units. Therefore, you are safe from any experimental bounds coming from proton decay. On top of that, you get as a bonus that there is a dark matter candidate there coming from anomaly cancellation, something that you didn't expect. And then the cosmological bounds tell you that you can hope to actually have if they realize at the low scale, and you can actually think about testing this theory. Okay. Then something that is very important is this signature coming from the new Higgs, due to the fact that you can actually have a very simple correlation between the Higgs decays and the dark matter study, because the theory is so simple that you can actually have this correlation. Typically, you could do that in other theories, but typically the theories are not so simple, or the correlation is not so unique that it's really difficult to make a unique connection between these. And as I mentioned, on top of that, I can have a production channel, associated production channel of the Higgs and the CV that is not suppressed by any mixing angle. I could have large cross sections, a large number of events. And again, 2 main scenarios which are interesting is that the production relation to 2 photons can be very large, or the dark matter could be more than 1. And at the same time, I talk very fast about the fact that this new theory predicts new CPU-related interaction, because you cannot redefine your fields and remove all the phases. And then you could expect the large value for EDMs in generically speaking. Of course, you cannot predict because you don't know the value of the phase, but the phase is more than 1. The fact that the new fermions generating EDMs are 2 loops, they cannot be super heavy. Generically speaking, you could have large value for EDMs. Thank you very much.
Okay, thank you for nice talk. So now question time. Is there any questions?
I'm wondering about the baryogenesis. Would you remind me if this dark matter carries a baryon number?
Right. Okay. Let me go back to. Let me see. Let me go back to the, let's say, the model, and I can give you the. Oh, maybe yeah, here. Look, this is the very simple. You have just a local baryon number. Every multiplet has baryon number. Okay. Therefore, every new fermion has baryon number. Okay. Then you break baryon number, and what you find is that the Liles neutral fermion in the theory is always stable, because there is a C2. You don't impose the C2; it's just coming from the gauge symmetry. Okay. And then the answer to your question, yes, every fermion has baryon number. However, after symmetry breaking, the important thing is that the dark matter has interaction to the U1 gauge boson. And this is defining the whole dark matter phenomenology in the theory.
Yeah, what I was wondering is that whether dark matter sector carries a baryon number and store them until it's freezed out. So
okay, very good. You are wondering more about the baryogenesis part, right?
Oh yes.
Okay, very good. What happens is the following. This is it's very important, because for a long time, even from the beginning when I started thinking about that, people thought that you could not have baryogenesis. Huh? Okay, here you have to think about the following. You have the standard model sector, and you have this new sector, right? Then when you say that U1b is baryon number and it's a symmetry before symmetry breaking, you have to think about the whole theory, okay? Now, this doesn't mean that you could not have asymmetries in both sectors, in the standard model or in the new sector, okay? This is the first thing. And then on top of that, there is something more. Suppose that you do leptogenesis, you do a some scale, you have a primordial B minus L asymmetry, okay? What happens with that asymmetry is that you have to check all the interaction in the theory and make sure that you study the chemical equilibrium equation for the chemical potential. And what you find is that even if this U1B is broken at the low scale, the baryon asymmetry today can be connected with the primordial symmetry, but the conversion factor is not the conversion factor that we have in the standard model when we do leptogenesis at the high scale, and you have a conversion due to the the standard model, as Faller's process. This means that you can have, this is the best way to prove that you can have a consistent scenario for baryogenesis. Now, you could think about electroweak baryogenesis, which is something that people from Fermilab study in the theory. Is that you break this U1B, but then you have a new Higgs. And as I explained, there are new phases in the theory, which, as you know, we need that for baryogenesis. So the standard model doesn't do a good job. And then you can study electroweak phase transition, the electroweak baryogenesis at the low scale. And this has been done, that works. You have enough freedom to change the phase transition. However, there are some small, but I would say generically speaking, works nicely, even electroweak baryogenesis at the low scale. Then you could have these both things, okay? But let me emphasize, the fact that U1B is broken at the low scale, this doesn't mean that you could not have a consistent scenario for baryogenesis, okay?
Yeah, but in that case, the leptogenesis you just explained, the CP phase you also explained is irrelevant for the leptogenesis in that case.
Right? No. In the case that we are publishing soon, it's different because this is a more ambitious program. Let me explain what I mean by that. If you think about baryogenesis generically speaking, no? We know that there are two main ways to do baryogenesis. One is, let's say you break lepton number from high scale, whatever scale, or it can be even low scale, and then you can convert this lepton asymmetry. Typically, it's better to use the language of B minus L asymmetry because it's a symmetry that is protected, and then you generate the baryon symmetry from that, okay? Or you can just have old-fashioned baryogenesis mechanism where you just break baryon number in some ways, and there are many mechanisms on that. No? Now, what is nice about these theories is that with the same representations, these four representations, I can gauge baryon and lepton number. Okay, this means that when you do, for example, when you do leptogenesis, you don't really know. You have to assume always that there is some initial conditions that we don't really know about if there is a lepton symmetry or baryon symmetry primordial even before the mechanism. Here, the nice thing is that U1 and B, they are conserved symmetry at, let's say, at the high scale, okay? Then you break L, and then here, the only thing extra that you have to put apart from the fourth representations are the right-hand neutrinos. Together, you can cancel all the anomaly for L and B. Then you break L, you do leptogenesis. Then dark matter doesn't allow you to go too high when the U1B scale. And then you know what is the B minus L asymmetry produced, but the chemical equilibrium equation tells you how much asymmetry you will put in the quartz sector, in our sector. And then you, in the consistent way, you can prove that you can have a consistent scenario for baryogenesis. You can see actually already here. This is a B minus L asymmetry at the low scale. And then the conversion factor is very, it's no more than one, but it's not too large or too small.
Yeah.
And then this is how it works. Okay, here you can control all the two scales. Okay, generically speaking, you always have to assume, okay, maybe there is no asymmetry, or maybe no, here the two symmetries are controlling. You can lower the U1L scale if you assume something like resonant electrogenesis. I personally don't want to assume anything like that. I just want to assume the standard vanilla electrogenesis. And here the right-hand neutrinos are feeling the new force, and they will try to wash out my asymmetry because they try to put the right. And this is the idea. Okay.
Yeah, and what I was trying to say that in this the figure on the right, the epsilon 1 is supposed to be a CP phase in generating the Rifton asymmetry in a N1 decay, right? Yes.
Yeah, right. This is
the CP phase is relevant for the previous one. The CP phase shown in the previous slide.
No. There is a mismatch. This is the usual CP phases that you have in type 1C. So generically type 1C, so the Yukawa couplings can be complex. Then this is not the CP violate phases that I was talking about. That is in the new.
That's exactly what I was trying to say. So the EDM you predicted is not related to the baryogenesis.
Oh, in electrogenesis, no, but in electroweak baryogenesis, something that we are doing.
Yeah.
Yes. Okay, that's but it's very important always. It's very important if you have a theory and you are predicting new CP violating phases, and the new degree of freedom cannot be super heavy. Better you check that everything can be okay. Okay, because of course I can put phases to 0. But I mean, if, for example, what you find if you do electroweak baryogenesis, these phases are very important. And the reason why I didn't mention this study is because there is a conflict between the EDM prediction and the whole story about electroweak baryogenesis. But it works, okay? This is what I can say.
I see. Yeah, thank you.
Hello.
Hi.
Hi. So thank you very much for nice talk. And I have a very simple question about this G2 symmetry, which is an accidental symmetry of your choice of the field content and the gauge charge assignment. So is this G2 is stable up to how many dimensional operators, or is absolutely stable, or?
Very good question. Before I answer this question, I would like to emphasize the following. I am not choosing the baryon number here. What I mean by that is that we try our best to cancel all the anomaly with the minimum degree of freedom, minimum number of representation, okay? And then what we find is that if you don't want to have any stable charge field or anything here, the baryon number for this new force representation is predicted equal to 3/2, okay? I have no choice here. You can put, if you check our papers, we try to find every possible solution, every kind of assignment, anything, okay? Because we want to make sure. It's not that I have the freedom to say, oh, it's 3/2. I don't have that freedom. Anomaly cancellation, that is why it's so important to think about symmetry of the standard model. It's so constrained that I have no choice, okay? Therefore, the first comment is the baryon number of this force representation is predicted by anomaly cancellation. I have no choice, okay? Now, on top of that, this is very important because if you know, I cannot make the point that in the minimal model, baryon number is broken in 3 units. If this can be anything, I can break in any units. And this is not happening here, okay? Now, as you said, after symmetry breaking, the U1B is broken to C2, okay? But now the question is, how many high dimension operator I can write down that could spoil the stability of the dark matter, okay? Now, the fact that this is the fractional number, 3/2, there is no way that I can write the high dimension operators. Think about the standard model. I have baryon number only in the quark sector. When you take into account the fact that you have to write SO2 in baryon and U1B, there is no way that I can write down a high dimension operator that compensate the 3/2 and destroy the stability of that matter. This is very powerful. This is a stable at any level. You can write any high dimension operators and you never will find any that will destroy the stability of the dark matter.
Okay, thank you.
Okay, any other questions? Yeah, okay. If let's thank you speakers again. That is the end of the today's seminar. So thank you for
Thank you.
listening.
Thank you.
Thank you.
Thank you. Thank you very much for the
Yeah,
invitation.
thank you. And I hope you stay healthy and safe and see you
Thank you.
around.